our webinar, Railway Electronics. Thank you for joining us. This webinar is being given by MET Laboratories. MET is a leader in the testing of electrical and electronic equipment for environmental hardiness, product safety, and electromagnetic compatibility. MET operates world-class labs in Baltimore, Maryland, Santa Clara and Union City, California, Austin, Texas, and also runs operations in China, Taiwan, Korea, and Italy. This webinar will run 30 to 45 minutes with an additional 15 minutes for questions and answers. Due to the number of registrants, all attendees will have their phones muted. If you have a question, please type it in the questions area of your GoToWebinar control panel. We will attempt to answer all questions at the end. Just a quick note on other upcoming events. We are hosting a safety certification sign shop webinar on December 16th, and you can go online to register. Today's webinar is being presented by Assad Bajwa and Alan Kamani. Assad is MET's EMC Lab Director, and Alan is the Lab Manager of the Environmental Lab in Baltimore. At this point, I will hand over the presentation to Assad.
Thank you, Sarah. Thanks, folks, for joining us. My name is Assad, as Sarah mentioned. I'm working in the EMC arena for almost over 17 years. EMC, special focus with railway, is one of my specialities. So the goal today of this presentation is to talk about where the applicable standards, especially keeping in mind the European requirement from EMC's perspective for when it comes to the railway system, rolling stocks, talk about the infrastructure, talk about the signaling and communication equipment and whatnot. So we'll try to cover all the above. Just a brief introduction. If you look at the conventional railways, which were based on like a century ago or more, steam engine, diesel engine. So traditionally there was very little electronics or electrical engineering involved. Majority was mechanical. That's where the word engine or railway came from. However, over the years, in last, I would say, 15, 20 years, more so, the way with the advancement in the electronics communication systems, high-speed communication, microwave links, and whatnot, also with the usage of the electrified railways, the EMC and EMI are coming more and more prominent issue when it comes to the railway and railway infrastructure. At the same time, as I mentioned, people are switching more towards the high-power-based railway, electrified railway system. So that adds to the concern, because when you're switching the high-power currents at higher frequencies, that give birth to, by very definition of the Faraday's law, huge emissions, which could interfere not only with the electronic and communication system within the railway, but at the same time, they could interfere, cause serious interference for the neighboring equipment in the area. Historically, there had not been a very focused discussions about EMC and EMI when it comes to the railway systems. Up until recently, large number of folks will rely on standards like EN50121 and or EN50122 to cover various aspects of the radiated emission and or the conducted emission. However, back in 2000, the European Union came up with a harmonized standard, which is EN50121. We'll look at what EN50121 covers, various sections of the standard and how they apply, and talk about some other EMC problem as we go along the presentation. Why the EMC is important for railway, I briefly mentioned in my intro, but one more time, the EMC in railway is not only about the compatibility with the standards, it's more so concerned overall with the overall concept of what we call RAM, or reliability, availability, maintainability. By very definition, if there are emission concerns, there are immunity concerns coming from the various electrical and electronic system being used with the electrified railway and or the communication equipment and or the signaling equipment, not only those issues, if they are not correctly mitigated, and or if they are the systems on the railway are not correctly designed to, and they are not hardened to deal with these with threats in the railway system from EMC EMI perspective, that will directly tie into the lack of reliability. And if the system is not reliable, availability will become a big question mark, and maintainability will be even a bigger question mark. And when you tie these things together, indirectly, all of that will factor into safety. However, keeping in mind there are other safety standards which will cover various different aspects of safety. My point here is that by not paying attention to the EMC when it comes to the railway system can lead to all the problem I mentioned, reliability, availability, maintainability, which ties into the overall safety of the operation. Before we jump into the standard 50121 and talk about the specifics of the various sections and what tests are called out, I think it's prudent to briefly talk about and draw parallels, if any, with the EMI environment or electromagnetic compatibility environment when it comes to railway, with the EMC EMI environment when it comes to the other products or other areas like commercial applications or enterprise applications or consumer arena. If you look at the electromagnetic environment, there are three main segments which either are contributing directly or indirectly to the overall EMI scenario. So by very definition, the rolling stock, which are your either electrified railways or even the diesel engines, which are running on the tracks back and forth, and mind it, considering the railway structure in Europe and in USA, the tracks in a given country could be up to thousands of miles long, depending upon how elaborate the railway structure is. But historically, a majority of the nation in the world heavily rely on the railway system. So by very definition, the emission from the rolling stock becomes one of the major factors when it comes to the EMC EMI problem. Infrastructure, as I mentioned earlier, in today's world, people are heavily relying on the computing devices, the controllers, the signaling devices, the communication devices, the devices to control start and stop, to detect if there is a vehicle or a train coming on the track. There are hundreds of different controllers, communication devices used today in today's infrastructure, which helps keep the railway system running. So those electronic equipment are another major factor which heavily influence the EMI environment for the overall railway setup. Then the third major factor is the neighbors to the railway facilities. There will be cell towers. There will be folks around the facilities or within the railway facilities and or on the railway trains who would be using tablets, laptop-like devices, or cell phone, or somebody is using a walkie-talkie from the security perspective. There will be there could be many other examples where there are electronics equipment being used in and around the railway facilities, which is not directly tied into the railway infrastructure. So that is another major factor. So when we look at the overall EMC concept, and we are trying to say that the railway system should be compatible, or the components of the railway system should be compatible, what it means is that not only the railway components, call it rolling stock, call it the infrastructure, not only they need to be compatible with each other, at the same time they should be working in a fashion that they do not interfere with the equipment or devices, electronic equipment and devices in the neighboring areas and or the folks who are using these facilities. At the same time, the railway system needs to be hardened and designed in a fashion that they are hardened enough not only to self-sustain the EMI problem caused by themselves, meaning by the noise coming from the tracks and other equipment, but also they should be able to handle the noises, immunity, and other problems being caused by the devices in the close proximity of the railway system. Some of the major challenges as I mentioned earlier, the railway environment is different from any other facility or area by the concept that the railway tracks are miles and miles and miles long, in some cases thousands of miles long, where we have two metallic rails going parallel to each other. In many areas, there could be several of those railway tracks running in parallel, especially in the railway facilities. So we see two very unique problems which happen with the railway system, which we don't see as prominent when it comes to the EMI on a board level or on a component level, and even in the field for other areas. Even give the example of the telecommunication facilities or cell towers or whatnot. So these two unique things are what we call longitudinal voltage, and other is the leakage current. The longitudinal voltage happens due to the much longer tracks, which when there are faults on the tracks, that voltage gets developed and it finds its way into the it will induce the current which will find its way into the railway system. The other major effect is the leakage current. When the leakage current happens, it's going to give rise to the induced currents, which will induce harmonics and subharmonics into the railway system. They can distort the power waveform, which can cause and lead to many other problems. So when looking at the EMI for railway, these two unique aspects need to be very seriously considered, one being the longitudinal voltage, other being the leakage current, and efforts are done to mitigate the problem coming from these two as much as possible. Diving straight into EN50121. EN50121 basically lays down the mandatory requirements when it comes to the railway application. I briefly mentioned that it will cover the traction of the rolling stock, which could cover both diesel and electric locomotives, the mainline vehicles, the urban transit, and if we look deeper into the various sections of the standard, it covers very well the signaling equipment, the communication equipment as well. So let's look further. The scope, as I mentioned, we want to ensure, if I could summarize the scope of the EN50121, in a nutshell, the intent there is that not only the railway facility, which we call infrastructure, rolling stock, which are the trains which run, or other trains which run on the rails, and the neighboring environment, they are compatible with each other. They can bear the noise coming from one of these components. They can handle it. They are designed in a way they do not go into what we call a service affecting response and or degradation of performance. And at the same time, they do not emit harmful noise or emissions, either radiatedly or conductively, which could cause interference with the equipment within the railway system and do not affect the neighboring systems around the railway facilities. I mentioned that there are various parts of the EN50121. So -1 basically gives out the definitions, like what is rolling stock. It will talk about various different environments. It talk about the generic limits and whatnot. So the -2 basically covers the emissions only aspect of the whole railway system. Down through my presentation, I believe I have one picture to show how those emissions are taken. So -2 will cover the overall emission from the system. The way people typically do is that a length of the track is identified, and using various different antennas, the testing is done. Typically what we do is on an empty track, we establish the ambience. Then we do with the train or locomotive moving on the track at a slower speed than we do at the standby mode. So various aspects of the emission are determined by testing in field on the tracks when the compliance for 50121-2 is being sought. Then -3-1 covers the rolling stock. If you look at the scope, it states that it covers both emission and immunity, but if you look deeper, -3-1 does not talk about immunity in the sense that it defines that it would define a test methodology. However, only thing it states is that it's assumed that by ensuring the emissions are kept low enough, and by the analysis that the components are hardened enough, it is determined that the product would be compliant to the immunity aspect or not. However, if you look at -3-2 and -4, they very well cover the immunity as well as the emission. And I have one more slide which talks about the little bit of detail about these immunity standards. And the immunity standards are very similar and based on the generic the immunity standard which are covered by for European aspect the EN 61004-4-X series. So we'll talk about that briefly when we go through further through this presentation. So as I mentioned earlier, the 3-2 and -4 would cover both emission and immunity aspect of the requirement for the railway system, and -5 predominantly cover for the fixed power supply installations. While we are talking about the railway EMI, and with the main focus, the main concern there is that the way the railway structure is, especially for the electrified railway system, we are talking about switching very high voltage, very high power system, and both these two, high voltage and high power, ties right into the cause of the emission, which is basically, if you look at the Faraday's equation, the EMF is directly proportional to d phi over dt. So higher voltage, higher current, higher power, and you just start switching those things, it will give birth to practically infinite amount of emissions. So having that said, let's look a little deeper for various different components of this of the railway system. What are the root cause of those? What would be the root cause of those emission problem, and what components will contribute to that? Just to give a more clear idea, when we look at the electrified railways, there are two main categories: the DC systems and the AC systems. The DC systems can have the very high voltage systems, which can be up to 3,000 volts. The medium voltage system can go as high as 1,500 volts, and the low voltage system can go from 600 volts to 1,400 volts. And in the AC systems, typically the power frequency remains 50 hertz. For if the system is based on the industrial frequency application, however, the voltage can go as high as 25 kilovolts, and that's for AC systems. In the lower voltage, lower frequency systems can be 16.7 hertz and 15 kilovolts. So just to give a general idea, when we are talking about the commercial IT equipment, the considerations are totally different because the threats are very different. Your input power voltage are very different. The environment where you are using those equipment are very different. However, when it comes to the railway system, just by merely looking at the input power for various systems within the railway, we can see the threat is very, very different, and it will need different consideration to tackle that. Oftentimes, we get the request where the manufacturer in the industry would want to have their products which been in the past tested to the commercial standard or IT standard or similar standards, and they want to have that product compliant by similarity to the railway requirements. And my argument always is it's a good idea, and we highly recommend that you review your design to ensure that your product is hardened enough to manage to survive without any degradation of performance in a railway system. And if we look at the levels for the railway standards, they are significantly higher compared to what would we use when we are testing IT-like products. So without further ado, coming back to the sources of emission, looking at the rolling stock, the main sources could be coming from power electronics, They could be arcing due to the current collection, AC-DC inverter, power supplies, lighting inverter, Wi-Fi motor, so on and so forth. And nowadays we are seeing more and more Wi-Fi-like devices people using. People are using tablets, cell phones, so on and so forth. So from the rolling stock aspect, those would be the major contributors to the noise for emission, basically. For infrastructure, similarly, there will be signaling equipment, there will be processing devices, there will be digital computers, there will be PLCs. If you look at from substations perspective, there will be rectifiers, switch gears, lighting equipment, public address system, and cordless phones, walkie-talkies, so on and so forth. So nowadays, as we all know, that almost everything is based on the electronics or wireless. Or the trend is to go more and more towards the wireless communication. So those things are very, even though from one angle to look at it, they are helping with a lot of things, but at the same time, the EMI problem gets more and more complex. External sources, we've been talking about this. Could be talk about the cell towers, talk about people on the phone, talk about the facilities. There is maybe a hospital close by. There is an MRI machine going on there. There could be external lighting strikes, so on and so forth. So there are tons of other sources outside the railway system which can contribute to the EMI problem. The EMI testing. As I mentioned earlier, 50121-3-2 and 50121-4 talk more about the immunity and emission. -2 and 3-1 predominantly focus on the emission only, with the -2 for the emission for the overall railway railway system. So the picture I have on the top shows when a rolling stock was being tested on the track in the field, and as I mentioned, the way the testing is typically done from the radiant emissions perspective in the field, the testing folks will initially determine the ambient. From there, they will go look at the overall track, where they will run the train in either on the standby mode or in a slow speed, and try to determine the overall picture of the emission coming from the track. And this testing is repeated at various different sites, different lengths of the railway track. That being said, the biggest challenge there is to cope with the ambient, considering there are, in today's world, so many, the ambient noise is so high that it becomes a nightmare to find a spot to deal with the ambient issue and get the good, decent data. So it takes repeated efforts, various times of the day, to find a time where the ambient levels are lower and testing could yield more meaningful results. We always prefer to do testing in the chamber to get rid of the ambient noise. However, it's not always possible, especially when it comes to the overall railway system, where it's not even possible to think about. Hard to imagine that one could put the overall railway train into the chamber. It's practically impossible. So the field testing we still end up doing. However, there are obviously challenges, and we find the way to deal with those challenges. When it comes to dealing with -4 and 3-2, the immunity requirements are, as far as the test methods are concerned, very, very similar to radiative susceptibility testing, which is called out by 61004-3, or conductive susceptibility, which is called out by 4-6, EST 4-2, surges, EST, the magnetic susceptibility, so on and so forth. That being said, the test methods are very, very similar. However, the levels of the immunity are based on the environment are way too higher compared to as if you were testing a commercial product for an IT-like standard. I mentioned that for -2, EN50121-2, we end up doing a lot of field testing. So this is one of the examples where you can see in the picture a substation is being tested for the low end of the frequency, where we are going from 9 kilohertz to 30 megahertz using a loop antenna. So part of the -2 testing, we end up covering not only low frequency, we go all the way up to 1 gigahertz. In addition to that, we do other tests which will include railway touch voltage, longitudinal voltage, surfometric voltage measurements, so on and so forth. So based on these measurements taken in the field, the collective compliance of the said railway system is determined. I wanted to include this picture and a brief description for everybody's interest. The idea is to talk about Pantograph Arcing. We talked about other sources of noise coming from the railway, the electrified railway, the high power system, the switching, communication equipment, signaling equipment. But one more major factor which adds to the overall noise into the railway system is the Pantograph Arcing. So when a pantograph, when a railway system, electrified railway is moving, the pantograph is touching for power the wires overhead, and depending upon how smooth the contact is, arcing could be very minimal to very prominent, especially when the railway tracks are old and they are not very well leveled. Then whenever there is a jolt which leads to the moment between the wire on the overhead wire which is supplying the power, the feeders, and the pantograph, people can see a very prominent arc going on, and that arc is basically hundreds of frequency components going very, very high in frequency, and these are what we call transient emission. But these transient emissions are happening almost all the time because of the mechanical movement that the train is moving on the tracks, and the pantograph is touching the power line, and it has to touch that. So those transient emissions are always there. However, depending upon the scenario, they could become more prominent or less prominent. MATLabs want to talk briefly about our capabilities when it comes to the EMC of the railway, and at that point I will conclude my presentation. We have 4 laboratories where we perform the EMC EMI testing. As Sarah mentioned earlier, Baltimore, Maryland. Then we have 2 facilities in California, Santa Clara, and Union City. And then we have 1 more facility in Austin, Texas. From all these facilities, we offer the EMC EMI testing services for a very diverse variety of equipment. We specialize into the railway testing standard. I mentioned typically we get the request to test to is 50121, and the parts of the 50121 time to time as part of the requirement, especially when we get a request to test for 50121-2, we do go in the field and perform testing in the field, which has its own challenges, but we have a team of very enthusiastic engineers who specialize in this area, and we've been working in this area for quite some time. At this point, folks, I want to thank you one more time for joining us for this webinar. I'm going to hand the control back to Sarah and Alan, and I will continue with the environmental portion of this presentation. Thank you. Thank you very much.
Hello again, and now over to Alan for the ESL portion of the webinar.
Yeah, good afternoon, everyone. This is Alan Kimani. I'm going to be covering the environmental portion of this railway electronics testing requirements. The first thing to mention is the reference standards that cover the environmental in this case being the thermal, humidity, weathering, vibration, shock, effects on products is covered by the EN50121, 5125-2, and 5125-3, depending on the location of the product. -1 covers the onboard equipment and the rolling stock equipment. -2 covers the standard installations, and -3 covers mainly the telecommunication equipment. I'll be trying to go through this overview and just generally give you an idea of the thermal expectations, humidity profiles that are required for equipment intended for railway use, the weathering test, the shock and vibration profiles that equipment is expected to survive, and in addition make some suggestions of ways to identify flaws probably in the design, or working on making the designs more robust using the HALT, which is a highly accelerated live testing method, and eventually cover do a reference, as I've mentioned, some of the standards that are referenced in the EN50121. Talk about the customer test plans, because in some cases, as we know in today's industry, it's new technologies going into this area, so some of the locations may not have defined parameters, and that the specs allow for mitigation or concession between the buyer and the product manufacturer's recommendations as to what's appropriate evaluation or assessment of the product. Finally, we look at some typical failures that we've come across over time, and I'll give a general overview of MET's capabilities with regard to the environmental simulation lab. So thermally, the operating range typically for most of the industry standard lies between -40 to 71 C. This is typically would cover equipment that would go into any location, whether it's external or internal onboard equipment. This gives pretty good margin and confidence for most manufacturers in terms of their products' ability to operate within the varying temperatures that it may experience throughout its life cycle. In many cases, like I reference here, case temperature, this is electronics that may be put in what they call cubicles. It's an electronic enclosure. The max for that, which is an ambient surrounding that, would be about 91, this being very extreme short-term exposure. But this can also be done for added confidence to determine and figure that the product can actually survive. On the next slide, I have a table of some of the typical thermal ranges. The EN50125 classifies products depending on the region, but typically the extremes are given here. Like for instance, the T2 would be from -40, and you have your short-term upper limit going up to about 70, which is depicted on the fourth column. The X on here depicts special conditions. Again, like I mentioned earlier, in some cases you have instances where the region of installation may not be clearly defined, may be new in the industry. So this would come up as recommended values, or maybe new field data that has been acquired that can be used for that. If none is known, then the standard says at a minimum you test to these ranges that are given. One, the industry standard, the lowest would be -40, and on the upper limit at for short term would be 85 C. In addition to the temperature ranges, equipment is expected to also comply with the varying humidity conditions that are observed. Sometimes this is all like through the year we have to go through the winter seasons and into the summer high humid seasons, and depending on the region of the world, like as I mentioned earlier, the railway systems are used all over the world, so you don't want to limit yourself to certain regions. You want to make sure that you're able to sell wherever the opportunity presents itself. So some of these suggested temperature ranges, depending on the region, sometimes we recommend at a minimum doing a 50-hour humidity test with the upper limit temperature of maybe 40 C at about 95%. That gives you clear confidence there's enough stabilization time for that test to assess a product and determine its survivability. Again, these tests are simulation of what would be expected in the field for products that would extremely see very severe, continuous, extreme humid conditions. We sometimes refer to the IEC 682-3, which calls for a much longer duration test, which is about 56 days, one of the recommendations we make here when liaising with potential manufacturers, with regard to a test like this, is just plan well. You know, in some cases you may be required to submit compliance documents within a certain time frame, so you want to have planned, you know, well in advance. You give yourself time to get through the assessment of a test with a long time exposure period such as this one. At MET, we always work with customers. We offer reviews at no cost to customers to assess and determine what is the most appropriate test. That can be done way in advance, liaising with our sales team and coordinating a time to come in. At no cost, we can do consultation, determine if this is the case, then plan, you know, way in advance and assist you with that. In addition to the humidity being one of the corrosion assessment tests also, the railroad standards also look at the weathering effects of products that are intended for installation on railway systems, depending on where they are. If you're talking about some signaling system, it may be, you know, always external, which means it's exposed to pollutants from, you know, salt mist to, you know, cumulative dust over time to, you know, sulfur from exhaust fumes from surrounding vehicles. There are test models for assessment of the product or survivability of the product to this varying conditions. Again, depending on the deployment areas. For instance, if we're talking about oil, it would probably be, you know, areas where it's close to maybe the engine compartments where there would be oil, this possibility of oil spillage. They could be within the, it may be on board and close to operators. Could be electronics that has to be, you know, operated or has to be used by an operator alongside beverages. So there's all sorts of assessments depending on the environment the product is in. I'm going to talk about some of the most severe in terms of corrosion, which is the salt fog. Salt fog test or salt spray. The EN50125 describes various environments and has a specific combination of salt and demineralized water concentration that has to be used for this test. This is mainly for products that will be installed externally, and depending also on the duration or the extent to which the particular product or electronics is vulnerable to salt mist, defines the durations given on here. You have a simple test that may be a 4-hour test, followed by maybe humidity storage for a specific amount of time. If it is extended or external, non-filtered air environments where it's going to be for extended periods, and you have a much longer durations that defined maybe 96 in some cases, depending on the customer and the region that the product is intended to be deployed. The durations may even be longer. The next slide, I'm going to talk about one of the biggest and I think the most critical in terms of survivability for most electronics going on to railway systems. This is the vibration and the shock testing. Being that if it's on board the locomotive, the level of vibration is severe and a lot of times can induce failures that may not have been picked out during the design phase, especially if it's a product that was mainly meant initially for a different market and is now required for application in the railway systems. The vibration and shock tests are defined. The 50125 standard references the EN61373 for definition criteria and levels of severity for the vibration test. That standard classifies, again, one of the biggest determinants is the region within which the component or electronics is intended for use. The table that I've just put up shows categories 1 through 3, which define the locations being either body mounted or bogie mounted or axle mounted. Axle being, I believe, in my opinion, the most severe because that's directly close to where most of the impact is being felt. At the body, there might be a level of absorption, but again, this defines what profiles your product will be subjected to based on where it's intended for location. The graph that I'm about to show details the frequency range within which the vibration profiles or levels that were shown in the previous table would follow. One of the key things for this particular plot, where I wanted to have it up, is also it defines ranges depending on the mass of the actual product or component being tested. When it is less than 500 kgs, you have your frequencies. The starting frequency would be 5, and your end frequency would be 150. And the heavier the product gets, heavier means sometimes it could be a system of electronics, it could be an air supply unit, could be a braking system that's been built, could be a telecommunication system that encompasses various chassis, so it has a different weight category. Depending on the weight category, the heavier it gets, the lower the frequency, the high-end frequency of the vibration profile is. The next slide shows the amplitude spectral densities for each vibration. And with this, one of the things I'm going to mention is that for the vibration and shock profile as defined in the 61373, there are 3 tests that have to be run. One is the functional vibration test that can be run depending on how long it takes to functionally assess the system that is under test. The minimum time for that would be 10 minutes. The maximum would be the time it would take to fully assess the functional or proper function of the product under test. The next would be the simulated long life vibration test. This one runs about 5 hours. That's the required. This particular slide, I show an estimate. We typically give an estimate of 1 hour for the functional vibration test. And to the right there, I just show one of our new electrodynamic shakers. That's an all-house Dickey that has a 3-inch peak-to-peak displacement. It's 17,000 force-pounds that we would use for this vibration and shock testing. Again, I'll say the simulated long life vibration test is a long duration test. It runs 5 hours an axis. So to complete the vertical, longitudinal, and transverse axis is, for that particular test, 15 hours. The standard also specifies the sequence in which the test must be done. The tests have to be done. One, you start with a functional verification, which is a functional vibration test. Then you have the simulated long life in all 3 axes, in the order vertical, transverse, long, followed by the shock severity, which I'll put up a table showing the various shock acceleration values depending again on the region where the product will be deployed. After the shock, then you do the final functional vibration test. From my experience, one thing I'm going to touch on is that due to the long or extended period of the long-term simulation test, the 5 hours, it is, in many cases, we see a lot of components either get dislodged from boards, depending on the design. Sometimes it's the mounts that have initially been used may not have been spec'd out for the particular weight of the product, or may not have the adequate displacement to allow for absorption of the vibration or shock pulses that get transmitted to the system. So this test is one that I find very valuable in terms of determining the integrity or the structural integrity of your system. Because typically, when you're selling a system to the railroad system, they'll tell you it's going to be mounted in this location. These are the mounting points. You have to build your system, attach the reference or the recommended connection tools or connection bolts, and they leave that to you, the vendor or manufacturer, to come up with a system that is going to be robust enough to survive the environment that they are putting this product in. So this test at least allows you to test the design of your system in terms of the enclosure, the mounting points, their ability to survive the environment within which they're intended to be deployed, and limits, at least gives you more confidence in terms of in-field maintenance, going in to provide or market a product when you haven't done this kind of assessment and ascertain that your system is robust enough to survive the environment that it's going to be deployed in, can sometimes be a costly mistake, because you may come back 6 months or 3 months later where you have to come back and do either redesign at cost, and then have to deploy personnel to go and do the field replacement or modifications to product. In some cases, it may not be fitting to the original design. So again, I say this is a real valuable test or assessment for products intended for railway systems. In addition to that, with regard to reliability, the HALT is highly accelerated life test is another one that allows, especially this is good during the design phase for the particular PCBs, which are the circuit boards that will be going into systems, electronic systems, maybe telecommunication or signaling. At the board level, during the design phase, this test is valuable in depicting or inducing failures that may occur, and gives confidence in terms of design. You'll be able to make designs early enough or design changes early enough to where you have confidence that on a board level, your design or your system is robust enough and has the reliability that is dictated for the field that it's intended. Again, this is just a picture here showing our HALT chamber. This is some other service that we also offer. In both coasts, we have HALT capabilities here in Baltimore and in our California facility. And again, it's a valued and highly recommended assessment or test for most manufacturers, especially if you're in the design phase and want to determine the reliability and robustness of your product. Also, coming up with built margins in terms of performance at extreme temperatures or transitions from one temperature to another. As you know, the train could be commuting from one region that's at extremely low temperatures to another that could be at ambient temperatures within short periods of time. So you want to make sure that at least your product can survive and will operate without degradation in performance throughout its life cycle. So this is a test that would really bring out some of that and give you a lot of added confidence that your product is designed and will operate reliably and has the margins built into it. Finally, I'll look at some of the standards that can be used as a guide. I've on occasion come across customers that are not certain what temperature profiles or what extremes to test to. On this, I've given one of the ones that I know is a pretty good tool, has a lot of temperatures, especially globally, gives a lot of data. Is the mill standard, the A10 gives a lot of guidance in terms of global temperature extremes, and the humidity values, that type of thing. So that's a good reference standard. The 61373, I touched on that. That's the one that covers and guides the vibration levels, shock values that are anticipated for railroad systems. The 5155 also covers electronics, rolling stock, but that merges into the 5125 that I talked about, has the different -1, -2, -3, depending on the deployment of the product. If you're intending to build for onboard equipment or rolling stock, then 125-1 covers equipment that's intended for those areas. The 5125-2 covers fixed electronic installations. Fixed meaning being fixed locations, and -3 covers equipment for telecommunication, that would be externally, and signaling systems, railroad signaling systems. So if you intend to build electronics or have a need to provide or supply electronic equipment for signaling or telecommunication within the railroad system, the 5125-3 would be a good guide or standard to look into. Finally, I'll cover a little bit of some of the failure modes that we see. On here I show a picture of a fractured weld. Same, that particular wedge like there at the end of that was mounted to a product, so it was being supported at the end to the right of that particular wedge, and the weight with the extended duration of vibration caused this particular weld to yield, and the customer had to go back and redesign and put a double-sided wedge on this for added rigidity and survivability of the structure to hold the system that was intended for sale to a railroad customer. The other failure modes that are commonly seen for temperature, especially if you don't have the margins built in, like I mentioned earlier, with the holes we test to extreme up to 200 degrees C down to -100 degrees C with transition times of 50 C a minute. You could test at component levels to make sure that your components will survive that. Typically, we see if some of the spec'd-out components were not well rated, or the design layout was such that the adjacent components were, emitting heat that exceeded components that had lower temperature ratings. You end up with overheating of the product and performance degradation. Corrosion due to humidity is seen that, again, depends on the finish of the coating or the finish of enclosures. This typically, if you're in electronic design, sometimes you find enclosures out there, ready market rated enclosures that are available. Those you would recommend for use. The only thing there is, again, thermally, you got to make sure that that enclosure in your product that's enclosed in that enclosure meets the range that I talked about in my previous slide. The vibration also brings, I mentioned here, solder joints. These are other areas that we see. You may have heavy components. In some cases, one case I saw contactors that had been, solder mounted and did not have, other additional fixtures to hold them in place. We've seen instances where those have come dislodged during the test, causing the component to dislodge, and therefore having discontinuity within the system where the functions of that particular system failed as a result of that. Finally, I'm going to talk about some of the capabilities, like I've mentioned throughout the slide. MET offers, we have a lot of capabilities in both coasts, East Coast here in Baltimore, in California, and also in our Texas facility, from temperature, humidity, thermal shock, be it multi-zone where you're looking at transitioning or simulating environments where you're transitioning a product from one extreme, 85C, for example, down to minus 40C in a given amount of seconds. We have multi-zone chambers that allow for transition and simulation of those type of environments. Temperature chambers ranging from 170C down to minus 70C, and also specialized capabilities for high temperature ratings of up to 350C, this depending on the application. In addition, we have for weathering simulation, I talked earlier about the salt fog. Salt fog is just one of the various weathering effects that products get to see. We have the sodium sulfur dioxide gases that also impact and sometimes end up non-metallic components can be highly degraded by exposure to this type of environments. We have chambers that can simulate that. Solar, UV, the xenon arc broad spectrum weather simulation chambers. If equipment is intended for maybe sitting above, it could be an antenna that has to sit outside. It could be a signaling system that is going to be seeing the solar environment for extended periods. We have simulators for that. We can simulate that and provide data to where we can assist even with the design, recommendation of products or color schemes that will allow for a better and more robust system. Vibration, we have electrodynamic shakers, we have hydraulic shakers that have the large displacement, especially for large heavy equipment. We saw there's some going over 500 kgs. We have hydraulic shakers that can handle that payload. We also have shock machines to simulate the shock environment. We have the ASCO machine that can simulate half sines, square waves, sawtooths up to 1500 Gs, depending on the application. So if any of these needs come your way, MET, we are here, the Environmental Simulation Lab. As Stan talks about the electromagnetic capability, please give us a call anytime. We'll be glad to assist you, meet with you, do a lunchtime review, assess your products, and recommend the test program for you. Thank you, and we'll open the question section.
Well, due to lack of time, we're not going to be having the question and answer portion. So if you have any questions, please email them to info@metlabs.com, and they will be answered. Again, all of our slides will be posted onto our website. So thank you for attending the webinar, and have a great day.